No. Okay, so just interrupted by the message from the Zoom.
Sorry.
So we need to ask the consent of all the audience who are participating in the Zoom meeting. This meeting will be recorded and put on our AI for your website. In case you don't want to show up more or less in this video, please simply mute yourself and turn off the camera. And now I would like to introduce Peter, who received the diploma in physics from Humboldt University Berlin in cooperation with Daisy Hamburg. And afterwards, he did the PhD degree in 2007 from TU Berlin. And in his career, he had experience in wireless communication, signal processing, information, and communication theory, applied math, and data science at the different stations. And I got to know Peter via the DFG priority program, compressive sensing in information processing. This is more related to compressive sensing, where we are collaborating in one of the projects. I got to know that Peter is an expert in applied math and also for all these kind of complex optimization problems. And he is invited to join the Future Lab as an expert, exactly to address the uncertainty topic, which requires actually a profound expertise in all the fields, what we have mentioned earlier. And he now joined us from the beginning of this year. And we are very much looking forward to have a lot of collaborations with him. And today he's giving a talk about his research field. And with this is also invitation to all the guests to get in contact with him and collaborate with him. Peter, now floor is yours.
Okay, thanks, Chang, for the kind introduction. Welcome everybody to my talk. I'm with the Communication and Information Theory Group at the Technical University in Berlin. There we try to solve problems which are relevant in future telecommunications. In particular, I focus on inverse problems like compressed sensing. I'm also involved in several cooperation projects related to computational imaging and also recently into problems in pool testing for COVID-19 testing. So I'm very happy to join the lab. And for this talk, I decided, instead of giving a technical presentation, discuss a few ideas how artificial intelligence can be potentially combined with inverse problems. So inverse problems are about, given the effect, find the cause. Inverse problems have a long history in physics, optics, imaging, and many engineering disciplines, also communication engineering. And the task is always, so I hope you can see my pointer here, the task is, given an observation and a partially known forward model given by an operator A, find the cause, find an x such that a of x is close to y. So in this formulation, the problem is ambitious, obviously, and we have to require more. We have to require a structure, or we have to come up with a prior for x. So there are several ways to do this. So for example, one can promote structure via regularization, one option. Another option is to parameterize the data better, or additionally constraining the data. And sometimes we are lucky, and then we get a computational tractable algorithm, which we can use on new data to recover or to estimate the cause. This has been well investigated, for example, for sparsity or compressibility in some domain, or dictionary for low-rank matrices in other fields. This well-established theory has yielded to rigorous guarantees and many algorithms which we understand very well. There's a little bit problematic still the topic of tuning for non-standard noise models, for example, and the interesting topic of performance of convex algorithms versus non-convex algorithms, where you also need an initialization. This is always a little bit in discussion. But here now, what can we do if we have real data? So can we describe structure or tuning or initialization for a classical algorithm in a data-driven way? So data-driven is well known. So this is the idea essentially of the machine learning approach. And there instead, we have a training set. So calligraphic D, it's a pair of features and labels. And then we want to try to find a map directly, an inverse map over a class of possible functions, in a class of possible functions, which achieve a small loss, empirical loss over the training set. Again, this formulation is ambitious, right? So there is always the questions about local and global minimizers for this particular loss. And when we set up the function class, or if we wire the network, we already introduce a prior into the problem. So we have often a handcrafted network structure, calligraphic Q here, and this already gives a prior on Q, which what I learned recently is also known as the inductive bias. And then there's always a problem. Now, what is more important, training or this a priori structure? At the end, we somehow get by optimization, we get a recovery algorithm, so a trained network, which we can apply or to process new test data. So once we come up with the right choice for this structure, for this set calligraphic Q, once we come up with the right training strategy and we have some experiences how to select the hyperparameters, we often get excellent empirical performance. On the other hand, it's difficult to come up with strict guarantees in this setting. Now, the question is are there also combinations or algorithms in between? So where we combine a classical algorithm with some neural approaches. So this is the topic of this talk. So this outline, I will start with compressed sensing because I work a lot on this field. I will show you a little bit non-standard setting of compressed sensing where I discuss the problem of tuning. I give you an example from wireless communication, and then I will proceed and give you a few ideas how artificial intelligence algorithms or approaches can be combined with classical algorithms. So, and I called this neurally augmented algorithm. So this terminology was introduced, I think, by Max Welling. And I give several versions of it. Okay, so let me start. And let me start with compressed sensing, which is related to classical sampling or scanning. So here we have a following paradigm, well-known paradigm to Shannon and Nyquist and Kotelnikov, that if you sample a signal densely enough, you can perfectly reconstruct the original analog data. So this is the paradigm, and this is good, but we should always have in mind that the converse is not sampling below the Nyquist rate prohibits stable signal reconstruction. It is true if the signals of interest fill up a whole subspace, because then we also have noisy type signals in that subspace. In particular, it is also a philosophical question that data which we are interested in, need to have a certain structure, a certain compressibility structure, and these are often this structure is often nonlinear. So for compressible signals, this approach is not true. So let me visualize this for a very simple setting. Let's assume that we have a vector x, and the structure is that this vector is sparse. So this is one of the simplest structure. So essentially, this vector lives in large dimension n, but has only few non-zeros, k non-zeros. And then we follow a scanning approach. So we consider every coordinate sequentially. And at the end, this means our forward model is simply the identity because we directly observe the vector x. Now, obviously, the vector x was sparse. So then later, we can compress this vector in the order of k log n. But we should always have in mind to acquire this data. First, we have spent hardware and software processing in the order of n at least. And the question is, can we do better? And this is exactly the idea of compressed sensing. So seminal works go back to Candace, Romberg, Tao, and David Donohoe. And they ask, or in particular Donohoe asks, can we not just directly measure that part that will not end up being thrown away? And so this means we compress already during data acquisition. And this can be achieved, for example, or can be sketched here in the following way. So our forward model, called here S phi, automatically compresses during data acquisition our source vector x, and we have to make sure that our samples y, which are now live in smaller dimension, are sufficient or contain all the information to infer again on x. And for sparse vectors, this essentially selects few k columns from the matrix phi. We have to ensure that the corresponding submatrix is of full rank. Okay, now we have to compare two different support hypotheses to be precise. 2k columns, every 2k columns of the matrix has to be yield a full rank submatrix. Now, this approach is well investigated over has been well investigated over the last 10, 15 years. We have many theoretical bounds for many scenarios, algorithms, and an exponentially increasing number of applications. It has been extended to nonlinear observations, to other objects like low-rank matrices and other tasks. Again, let me recall that for certain noise models, the algorithms are still difficult to apply, and often one has to come up with complicated handcrafted tuning. Okay, so let me sketch a little bit how these rigorous estimates or guarantees look like. And so one has to describe a little bit more what is the requirement for this matrix, for this forward model. So in this case, phi, and now I call it calligraphic A. So our forward model, so we have to ensure, and this is called the null space property, we have to ensure that S sparse vectors are well separated from the null space of our observation map. This is obvious and intuitive. Once we have this, we can solve a combinatorial problem, so where we somehow optimize over all sparse vectors shown here in brown. So they are on the coordinate axis. We have to optimize over all sparse combinations which are feasible with our observations, or which are somehow pointing to this affine subspace here. This is an NP-hard problem, and one of the main results in compass sensing that this can be, once this condition is fulfilled, the null space property can be replaced by something which is a convex approach. And this is shown here. So you minimize the L1 norm. L1 norm is the sum of the absolute values of a vector. And what you do here is you shrink the L1 ball, and once you leave the feasibility set, you exactly point on coordinate axes which are related to the sparse vectors. So therefore, if everything is fulfilled here, you exactly get the sparse vector. Now, there is a guarantee, you can show a guarantee which looks as follows. So if you solve this problem and you have this null space property, then you can show that this convex problem, the recovery error scales with the noise bound. But there's a little bit difficulty here. So first, you have to know the noise bound. So this is a forward model. E is noise, epsilon is a noise bound. You have to give this noise bound to the algorithm, and then you get this noise bound as error. So this intuitively is problematic if the noise itself depends on the unknown, because then you cannot give such a bound. This happens, for example, in Poissonian noise, photocounting noise, multiplicative noise, and also in covariance matching. And I want to show you now that if you know that your data, your vector X, is also non-negative, in addition to being sparse, and your observation scheme, your measurement scheme, has an intrinsic bias, then you can overcome this difficulty. And this is a result. Again, you first need that your forward model has such a good compass sensing property, but then you also have to ensure in another property, which we call here M+ term. So this terminology goes back to Brookstein. You have to ensure that the row span of your observation map has to intersect the positive object. And then, in this case, you can solve a very simple problem. You simply minimize the residual over all non-negative vectors, and you immediately get a guarantee. You can compute this, which also scales with noise without knowing a bound, which you have to first give to the algorithm, because this algorithm or this convex program is tuning free. This is very useful in many applications. In particular, we applied this also recently to pooled quantitative PCR virus testing. And I want to show you now another application from wireless communication where we use this. The setting here is that in future we will have base stations in mobile communication which are equipped with many antenna elements. So this antenna has more than 200 receive antennas co-located at the same location. And then this antenna serves a cell with many devices. This could be cars, this could be smartphones, handhelds, smartwatches, etc. They are all registered in the network, but only few of them are active and want to communicate. They send a pilot signal to the base station, or they directly communicate by sending code words. And this setting is obviously a compressing problem because only a small subset of these devices are active during a certain period. So this is now a joint work in our group. And I want to sketch this a little bit. A very simplified linear model for this communication problem is as follows. If a device is active, it transmits a sequence of length small n to the base station individually. So this means we have a matrix of sequences. Every sequence is a column in this matrix. So and if the device is switched on, it selects its sequence, it's amplified and somehow transmitted to the base station. So this is a non-negative vector of a diagonal matrix with a non-negative vector on its diagonal. And then it is multiplied with a random phase. So this means on one antenna element, we receive a sparse superposition of these sequences. From compressing, we know that if we use a pseudo-random approach for these sequences, we have to ensure that n, the length of the sequences, have to be in the order of s times the logarithmic penalty. So s are the number of active services or users in the system. For example, here 4. And then we receive this on one antenna element, and this is noise. Now, the question is now, if we have many antenna elements, let's say 200 antenna elements, what can we say here about the scaling? So we have to solve a problem where we observe this matrix A, and we know only Z, and we only know the matrix A, and we want to know this sparse non-negative vector. And the idea is decode in the covariance domain. Covariance domain, this is called sparse covariance matching. And the idea behind that is that we see every column, every received signal per antenna as a new realization of a process with a certain covariance model. You can compute this under certain assumptions, and then the covariance model is that this is a linear function, a linear map, depending on a non-negative sparse vector, which is exactly the squared magnitude of this vector. Now, in practice, we have only finite number of antennas. So what we can do at the base station, we compute the empirical covariance. And with sufficiently many antennas, we hope that we approach the true covariance model shown here. But we should have in mind that the error here depends on the unknown vector which we want to recover. So classical compressed sensing algorithms therefore usually perform poor because they have to be tuned somehow. Okay, so this is a compressed sensing problem, a non-negative compressed sensing problem. And if you do all these theory, if you apply all the theory which I have shown before, and you do this for random sequences, what turns out is surprisingly, now you can support a sparsity in the system which scales up to n squared, which is a much larger sparsity you can support in the system. And this is, for example, shown here. So, for example, if your sequence lengths have 20 samples, so this, we call this often as a pilot signal, then we can support a sparsity up to 70. So here we have failure, here we have success. So this, from the compressed sensing point of view, this is somehow intuitive. From the engineering or communication engineering processes perspective, this is this yields to a new scaling law, which has inspired many follow-up works. Okay, now this was an example to show you a little bit how rigorous one can analyze compressed sensing problems. On the other hand, we want to approach problems where we don't know the forward model. Instead, we have only samples. So the question is, can we now combine inverse problems with data-driven approaches? So I already mentioned that one option is to use regularization. So regularization means that we have a data fidelity term and we have a regularization which promotes structure. Once we can compute this regularization in analytical form, we are essentially, we can say we are done. So we can at least approach this. But now what happens if we have a certain algorithm which implements the regularization? We cannot describe this in a mathematical terms. We only have, for example, a computer program which does this. For example, an algorithmic denoiser. Let's just assume that we have for a certain data set, we have an algorithmic denoiser which has been improved and trained and optimized over years to work exactly for this data set. How we can solve now, how we can set up a regularizer for an inverse problem now. One option, very straightforward option, is you build a regularizer, but by somehow regularizing with respect to the performance of the denoiser. If the denoiser performs well, then this means this is a feasible signal. If the denoiser performs bad, then this is probably an unfeasible signal. So this so-called net approach has been proposed by Lee and others and has been already analyzed from the theoretical perspective. But it's a little bit problematic because if we want to use this later in inverse problems, we have to compute gradients for an algorithm, which could be rather complicated. The question is, can we do something which works without gradients, without computing gradients of an algorithm? And yes, also this has been proposed in the literature meanwhile, which is called as regularization by denoising. So for certain denoisers, you can construct such a regularizer, and if you compute the gradient of this regularizer, then the gradient of the regularizer is related to the algorithm itself. So this approach has been proposed by Romano, and the theoretical justification for this approach, particularly all these assumptions, have been provided by Riehaus and Snyder 2-3 years ago. So this approach is super fast and super simple. No gradients have to be computed. It can be combined with plug-and-play algorithms like ADMM. You can use existing denoiser networks, for example, like denoising convolutional networks. Okay, but in practice, all these conditions are not fulfilled, but empirically, these approaches work very well. I already mentioned another approach, instead of regularizing, is to constrain the signal domain by data, by training data, from training data. And in particular, generative models have been analyzed intensively in the recent years for this approach. And they are known to work very well for complicated signal domains. So I think a very famous example is Stylgan. This is a generative model which has been trained by images from persons. And once after training, you can come up with a random point in the latent space, and this Stylgan gives you a person which does not exist, which has not been, which was not part of the training set. So training of such structures can be done via adversarial training or via the idea of autoencoders. So I think most of you know probably what is an autoencoder, a particular variational autoencoder. Just to remind you, what we have here is that we have a certain data set and we try to represent this data set in a lower dimensional latent space. So we train an encoder and a decoder pair such that this pair acts as almost as an end identity on this particular data set. If we follow the variational approach here, then this comes additionally also with some smoothness and regularity in the latent space. And this is important because later we want to use a gradient descent algorithm. So this means if you smoothly travel around the latent space, you somehow smoothly travel around your data set. And then what you do then is, instead of minimizing this objective over the data, you instead minimize now this objective over the latent space. Okay, so this has been analyzed already from the theoretical perspective, but I will switch directly to some experiments to not lose time. Here is a comparison of the different approaches for a generic data set for MNIST data. So the setting is that we have MNIST data, and from this MNIST data, we see only compressed observations. So we have a compression factor of 8, and the compression matrix is a Gaussian matrix. So this is the inverse problem task. Now reconstruct that data. If you follow a very simple idea, least squares or minimizing the Euclidean norm approach, then you see that this does not work. So this would be something like a linear filter, and it does not, it's not able to reconstruct the structure. If you instead regularize in the imaging domain, then we see that this compression factor of 8 is too hard. So even through the image may be sparse in the imaging domain, you cannot really recover the image. If you instead regularize a little bit more clever in the gradients, in the space of the gradients, so this is called the total variation regularization, then we see already that we, for example, at least we can classify the digits here. And here, for example, is shown the red approach with a denoising convolutional network trained on MNIST. I would say it performs a little bit, but not much better than the classical algorithm. Instead, the generative model approach, I would say, performs here at best, and we clearly see the ground truth. But we also see that, and this is due to the variational approach, that this is a little bit blurry. Okay, so far this was about linear models, linear forward models. Now let me come to a more practical setting, to a nonlinear forward model, and how their artificial intelligence inspired approaches can be integrated. And this is phase retrieval. So phase retrieval appeared historically for the first time in X-ray crystallography, and has now meanwhile many applications in optics, imaging, microscopy, tomography, and also communication, by the way. The task here is that the situation is that your detector is not able to measure phase. Instead, you only measure intensity. And then you have to solve maybe complex or real data X, but A could be complex, but the phase is lost. You set up this again as an optimization problem. So this is the data fidelity term. This is the regularizer, which promotes structure. And maybe if you know a little bit about spectral factorization, then you probably have in mind that the first characterization of uniqueness in this setup is due to Norbert Wiener about spectral factorization. But here I want to focus on the problem, on the optimization point of view for this problem. And you see already this problem is non-convex. But it's known that that descent algorithms perform empirically very well if you, and also provable meanwhile, if the initialization is very close to the optimal value. Now, the task is again to solve this problem, to recover X with as few as possible observations. And here now again, the autoencoder comes back to the generative model. What we analyzed here is the following idea. We set up the inverse problem with a generator, and we perform few descent steps on this objective because these descent steps are expensive. And then we compute it. From this, we get an initialization for a classical algorithm, which could be, for example, superfast randomized catch mark, to overcome the remaining error and to sharpen the image. Here's an example. Here are several algorithms, and here is the increasing sampling rate. So the model is, we have our intensity observations, we have a Gaussian matrix, a random Gaussian complex normal matrix. The sampling rate is the number of rows divided by the number of columns. The classical methods are shown here. So this is randomized catch mark alone with a random initialization, Wirtinger flow. This is a descent approach with spectral initialization, truncated Wirtinger flow. At the end, all these classical algorithms, they need a sampling rate of at least 5 to 6. Instead, if you use a generative model to perform everything. So this means many iterations, we see that this works very well. Already at very small sampling rates, we can somehow identify the ground truth. This can be speed up by only computing an initialization, and then we use a classical method, randomized catchmark, and we see we get essentially the same. It's a little bit sharper, but with a runtime which is by a factor of 100. So we improve by a factor of 100, and compared to the classical algorithms, we compare in terms of sampling rate by a factor of 6. So why we have analyzed this? Because we have an ongoing cooperation with DLR, Lasov, and Humboldt University, and we want to apply this for Terahertz imaging. So phase retrieval for Terahertz imaging. And here the task is a little bit more difficult. So we have a terahertz source, and we somehow modulate on this source via an optical switch binary mask. And then this mask propagates from the optical switch to the scene. And then after the scene, we collect all the radiation into one intensity value. Then we change the mask, we get another intensity value. We change the mask, we get another intensity value. This is the idea of the single pixel camera and compressed sensing applied for phase retrieval. The problem here is Terahertz radiation, and we have to take into account into the forward model several diffraction effects which could happen over this distance of several 1 to 2 centimeters. So why this is difficult? Because these masks getting blurry over these 2 centimeters. So if you start with such a perfect mask, then already after 1 millimeter, you see that the mask gets blurry, and more blurry, and after 2 centimeters, they are losing a lot of rank over this propagation distance. And this has to be included in the forward model. So this is the result. This is the ground truth. And now we have a standoff distance between the optical switch and the target of 1 millimeter only. We see here the classical algorithm performs well. The generative model alone performs not very good, but if we take this as an initialization for randomized catchmark, we get very good results, very sharp results. Now, if we increase the distance now, for example, to 2 centimeters, we see again that the classical algorithms, they get a problem whereby this hybrid approach can produce a sharp image. Okay, so this was about regularization and generative models as one way how to combine artificial intelligence inspired ideas into classical inverse problems algorithms. Another very cool idea is what I like most is the idea of unfolding or unrolling. And here the idea is that you have a classical algorithm and which you unroll and then you train it. So let me explain this again from the perspective of compressed sensing. So the task is again, we want to recover a sparse vector from noisy observations, compressed observations. And then there's a very famous algorithm in this field, which is called iterative shrinkage thresholding algorithm. And this is a particular version of Approximate algorithm. And they're all these algorithms, they have this particular form. What you do is you take the previous iterate and you linearly combine this with your measurement, and then you apply a nonlinear function component-wise to get the next iterate. And this nonlinear function depends on certain parameters. In particular, for thresholding, so for ISTA, this function zeroes out small components and shrink larger components. It depends on 2 parameters in this case. What you do then, you somehow unfold every iteration as a layer of a network. This has been proposed by Gregor and LeCun in 2010 and is known as LISTA, learned ISTA. So here, this is the first iteration, second iteration, third iteration. And what you do then, you have weights per iteration, and you have nonlinearity parameters, so the activation function per layer. And what you do then you train this computational graph by training data, by feeding in training data. So this, you can have, for example, a situation of shared weights where you somehow train these weights S, but they are all the same per layer, but you can have also individual weights, and you can also have individual parameters of the activation function. So this idea works for many algorithms. It has been applied also for ADMM, belief propagation, Bayesian algorithms, and even for trained denoisers, where this nonlinearity is again a network. It's very useful for data-driven tuning and acceleration, or somehow incorporating structure from the training data. Let me give you an example again. This is a cooperation with BAM, Bundesanstalt für Materialforschung, in non-destructive testing. So the idea is here that you have a material with certain defects. What you do is you illuminate random laser patterns to produce heat waves in the material. And these heat waves getting scattered on defects. And on the other side, on the back side, you somehow you take an heat image from the propagated waves. And then you change the random laser pattern and you do it again. So this is also known as the problem of joint sparsity, because for every measurement campaign, the locations of the defects remain the same. So this means you can also write down this as a convex problem, and then you can start to unfold this algorithm. This is a certain norm which somehow reflects or promotes this structure, this sparsity structure, which remains the same for every measurement. And the goal is obviously that you can now resolve something which was not possible before. So here's an example. This is the target. So here we see defects at different distances. And if you unfold this algorithm, this thresholding algorithm, block thresholding in this case, and you train, then you get the following result. So here we see again the ground truth. So these are the defects. A classical algorithm, which is already accelerated, is shown here in black. This is what you get. So this problem is difficult since we really have to model the heat wave propagation. So this is part of the forward model. And you need 500 iterations to come to this result. If you use a trained network, this can be, you get essentially even a better performance already after 6 iterations. Now, if you train such an algorithm, you have to train a lot of weights. And there was a cool idea which came up 2 years ago, which is called analytically, has been proposed by Leo and others. And they show that you can almost get the same performance if you instead train the weights, you compute them in an analytical fashion. So you have to solve this problem, then you get the weights, and you only train the thresholding parameters per layer. The nice thing, so first they showed that you get empirical, very good performance, comparable, almost comparable to the classical lister. But the nice thing about that is that you can also get a proof. So you can prove that under a certain condition on the trained variables, you can show that this trained network really has a guarantee. Unfortunately, to do so, to complete the proof, they had to assume that you have to take the worst case situation because this individual bounds depends on the unknown ground truth. And now, inspired by this idea, we came up with the idea, okay, let's see these variables as a time series. And we somehow have to predict the long-term behavior of this time series. So, and we use here the idea of LSTMs, of an LSTM cell to somehow inject certain variables which are available in the algorithm and to predict during the reconstruction of the test data to predict adaptive thresholds. So we called this newly augmented lister. And this performs surprisingly really good. Let me show you an example. This is again an example from wireless communication. So here the task is to estimate such an impulse response. So this is delay on the x-axis, and this impulse response is sparse, but it has also another feature that it's exponentially decaying in its second order statistics. And the goal is to recover this object given Fourier observations. So this means in the Fourier transform, so if you take the DFT, you can take samples in a certain allowed band. And so our forward model is then a partial DFT matrix. And if we do this, we see here the iterations or the layers. The classical shrinkage algorithm is shown here shown here. If you classically accelerate this to what is called FISTA, you get an improvement. But if you do this with this neural augmented ALISTA, you get already an excellent performance, and essentially it saturates already. It's a noisy setup, by the way. It saturates already after 8 to 10 iterations. So this was very impressive. Now, this was so far ways how to combine these from a non-Bayesian perspective. But all this has been done meanwhile and investigated also by iterative Bayesian-inspired algorithms. So in particular, in compressed sending, there's a very important and famous algorithm which is known as approximate message passing. Essentially, this is ISTA, shown here in black, but you add a correction, which is called the Onsager correction. The effect of this correction is that asymptotically, the iterates over the coordinates of the vectors decouple. So we call this in our field as the decoupled channel model. In particular, I have a very good theory, asymptotic theory, how you have to set up all the parameters if you use this algorithm in a classical way. But this algorithm has also been shown to be, it can be unfolded, and this is known as learned approximate message passing. And here the question is, can we somehow, so because you have to implement here a certain denoiser, which is usually related to the prior of the data. So the question is, can we somehow learn this denoiser from training data? And so for example, let's assume that our original data follows a so-called Bernoulli Gaussian model. So this means this is a strictly sparse vector, and on the support, the non-zero values are chosen as Gaussian distributed, independent Gaussian distributed. Now, if you start with ISTA, over the iterations, you get this performance. If you use a classical approximate message passing algorithm, you get this performance, because in the classical version of the message passing algorithm, you only assume that this vector should have small L1 norm. If you start to train these two algorithms, you get a trained ISTA with shared weights and a trained ISTA, or learned ISTA, let's call it learned ISTA, with individual weights. And if you do the same with ARM, you essentially get the best performance so far. So again, if you go here, if you compare this, so the plot on the right-hand side shows if we already would know that X follows a Bernoulli Gaussian model, then we also can set up the AMP algorithm, because it's a Bayesian algorithm. We can do this without training. We achieve almost the same performance as a trained algorithm. So this shows once you have perfect knowledge on the distribution, then the classical algorithm, a good classical algorithm, because it's known that AMP is optimal, you cannot improve this really by learning. But if you don't know the prior, then you can obviously learn from training set a match prior. And we worked this also out in a more universal setup for Gaussian mixture models. Okay, so let me summarize. We have, on the one hand, we have well understood algorithms. We have theory for these algorithms. On the other hand, we often use end-to-end learning, which needs many handcrafted tuning. And then if everything is fine, it works good, but we not really understand why it's good. Now, the question is, are there solutions in between, which we maybe better understand step by step? And this is the idea of neural augmented algorithms. So we take a classical algorithm and we replace small parts of the algorithm by neural components. Okay, to summarize, I started with compressed sensing, where we have all the theory. I discussed here also the problem of tuning, and there are tuning-free approaches for certain setups. And then I discussed several approaches. There are many more known in the literature meanwhile, how one can combine artificial intelligence inspired approaches with classical algorithms. And then at the end, I showed you another approach, which is called unfolding, which is very helpful to adapt or tune and accelerate iterative algorithms given by on the basis of training data. Okay, thank you.
Thank you very much, Peter, for sharing this comprehensive and teaching review of your research topics and their potential relationship and applications in our AI topics. Now we give way to questions from our audience. So please, if you have questions, please write the curator in the chat and I will give you a turn, or simply please turn your microphone on and ask the question.
So maybe I get started.
Professor Su, thank you.
Peter. So I'm particularly interested in this unfolding algorithms you presented. Do you see a way how could we somehow integrate uncertainty measures in the whole procedure in a way that not only that we are able to get a sparse reconstruction of the signal, but also when it comes to the position of non-zeros, also get a kind of uncertainty measure out from the system?
Yeah, so I think, yes, I think this is possible. In particular, one should have in mind that in Bayesian algorithms, so for example, these algorithms, you already without learning, you get a distribution, right? But you have to know, so everything should fit, right? So, and if you don't, if you start with a wrong prior, then also the predicted distribution is wrong. So, but I think that at least this is a good starting point. If you train somehow the built-in prior from training data, and then at the end, at least empirical. One has, I think it's very difficult to prove that, but at the end, you again get a distributional response, so which automatically gives you uncertainty. On the other hand, it's still open how good you learn this prior, right? So this is again the same problem as in all other machine learning tasks. Is that this is a critical question? But I think we should start with algorithms which we understand, and then we should go step by step. This is my opinion.
Yeah, I agree. And the good thing here is, as this kind of physical model-based problem, then it's also we are also able to derive, or for example, Kramer lower bound from the input
Yes.
data, and then we have a good reference to the uncertainty qualification to verify a bit.
Yes, agree. Yes, indeed.
Any more questions or comments? We still have a couple of minutes for proposing maybe internal discussions, suggestions, or collaborations.
I have one question.
Yes,
Richard, sorry.
Go ahead.
Hello.
Professor Wambler?
No. I didn't have a real question. First of all, thank you for this very interesting and inspiring talk. It's good for me to see that a lot has been happened also in the compressed sensing world. It was a little bit overshaded in my attention by the deep learning period. So this is very good to see. Also that the Terahertz work is going on in Berlin.
Yes.
This is also very good. So I did not really understand why this unfolding of algorithms is a kind of, if you go back to this slide, if there is a kind of linear network assumed. I mean, if it's an iterative algorithm, the natural way to map this into a neural network would be a recurrent neural network, not so to say, not an unfolded one with a finite number of iterations. Could you explain this a little bit?
Yes, that's true. You have this, in particular, for example, in this AMP structure, you have this recurrent structure, right? So because you always have such a side connections. It's true, right? This is an you can unfold this in such a forward network, but you always have these side connections.
Okay. But it's implemented as a kind of a recurrent neural network, or not?
This is what we propose. This is what we propose in this. Let me go to this newly augmented lista. This is what we propose, is that we really see this these thresholding parameters as a time series, and we try to predict the long-term behavior of this time series. So the time is here the iteration.
Okay. I mean, maybe I can add another more general question. It is for me, it was always interesting to see that this shrinkage algorithm. I mean, with the soft thresholding, it reminds me, of course, of the nonlinearity that we have in neural networks. Anyway, I mean, if you combine two of these ReLU nonlinearities, you get exactly this soft thresholding.
Exactly.
A transfer function. So sparsity and neural networks is another topic anyway. I mean, this particular choice of the ReLU, of the famous ReLU nonlinearity in many of the deep neural networks, of course, will cause probably also sparsity in the neural network itself. It's a different question, of course, not in the signal, probably.
Yes, indeed. This is also a very important topic, and there are also different approaches on this. So the idea is, can one come up with a network which achieves the same performance but which has much less connections, right? This is a very important topic if you later want to implement this on certain sensors or on certain low embedding hardware. You have to take care of that, but also there are two approaches, right? First one is you ignore this and later you prune the network. The other thing is you come up with a cool connectivity which is already sparse, and then you train on this connectivity. And this is indeed related to what I had on the first slide. This is related to this inductive bias. So what you do is that you optimize over, you first fix the network structure, and then you start to minimize the empirical loss. But setting up the structure, I would say I feel that this is even more important than training, because, for example, why this works so good on images, because we always know the decomposition in wavelets. And if you do this, you end up exactly by such convolutional networks. Right, so there is a connection, and this convolutional network is handcrafted. And this is exactly also the same for this algorithm. So it would be cool to, from the beginning, to sparsify such networks, and not later. Yeah, okay. Good question.
Yeah, but will be very important. I mean, also we will have to go also into the direction of green IT and edge computing. So we will always be asked, why do your networks, why don't they be energy, let's say, conserving? So this, why do we have such a big energy consumption in deep learning? This is already in the media. So we probably have to answer this criticism anyway. So the topic of sparse networks with only few parameters will be, I think, a very important one. Anyway.
Yeah. Okay. Yes, I agree.
No, thank you.
Okay, Peter, this is Yuan. I have one question. You're on the right slide. So
okay.
I'm just thinking about this this network, and also the recurrent network you showed. Basically, the network is training basically the model S, right? So we're making small adjustments in the model S.
Yeah.
And then the outcome is that we can improve the convergence. So I'm a little bit puzzled. Why is it like this? For example, I know the S very well, for example. Why do I need to make small miniature changes in the network, and then the benefit is I improve the convergence? Do you know?
Yeah, I think, yeah, good question. I think I know what you mean. So first of all, there are classical methods to accelerate such algorithms, right? So you can do this also via classical approaches, which, for example, is Pfister approach. On the other hand, for certain subclasses of data, you can do much better. Right, so the thresholding can be, so you can further accelerate an algorithm if you restrict the data or if you come up with a certain distribution of data. And so therefore, the acceleration really depends on the input distribution. And if you set up the algorithm and if you would know the distribution analytically, you can do also this via classical approaches. But if you have only sampled training data, then you have to do this with training data. And I think then this structure comes into the game.
Okay.
Does this answer your question?
Yes, I get that your point is basically depending on the data itself, right? This is what your argument. Yes. Okay, another.
Yeah, maybe just as an additional comment, I think the last slide was very short. If you know everything, if you know the input distribution, you can use, for example, the AMP algorithm, which is a Bayesian algorithm. And if you are able to compute the optimal thresholding function, and you put this into the algorithm, which can be done for certain examples, then you see you cannot improve via training. You are already optimal. But if you don't know this, you have to come up with something which can be trained based on training data.
Okay. Okay. And the other question is also again related to this S, and so yeah. For example, I maybe I had very bad. Better, and then the estimates are will not be very good.
Could you repeat? Sorry, your connection was lost for a second.
I mean, for example, we have a very bad batch of training data. And then this S in one of the iterations here is not very well trained. And then the estimates before the pass sign is not very good. And this error is being propagated afterwards.
Yeah.
So is that also correct? That
yeah, this happen? I mean, yeah, but one has to say there are, this is also a topic by its own, how to train such networks, right? So you can do this and you really see a difference. We played with that if you train layer-wise or in a hierarchical way, or if you train end-to-end. This makes a difference. So one option is to train the first layer, then to train the first 2 layers, then to train the first 3 layers, etc. So there are many versions of how to train that, and this makes really a difference.
Okay, right. And I'm just wondering, why do we give all the freedom to all the S here? Because they are somehow related, right? So, but in currently network, you basically allow the S in different layers just to tune by themselves.
Yeah, I think this is, yeah.
But it's always the same S, Aki. It's the same S.
Yeah, there are there are 2 versions. This is if you can have shared weights, right?
Okay.
Then you don't have this structure. You have this structure, but there you have also the option that you have individual weights. So this we call in this framework is called tight and untied learning. So there are 2 options, but I think. Okay, is this related to your question? So
yeah, I think so. So my question is just if the S are the same, why do we need so many layers?
Yes. Okay, then I understand. Yes. Yes. If S is the same, then we only change. This is called shared weights or tight learning in this setup, and then the parameters change from layer to layer. The denoising parameters, these theta parameters, the thresholding parameters.
Okay.
They change from layer to layer. The advantage is that you only have to train one S with shared weights. but you get better performance if you also have individual weights. So then really these layers make sense. Yeah, now I understand what you mean. And this is really difficult. So I played with some colleagues a lot about different learning strategies, how to train such a network. And this is there are many open questions.
Okay, great. Thank you.
So thank you very much again for the participation. Thank you, Peter. We wish you a lot of success and fruitful collaborations with our colleagues in the lab. To all attendants, and thank you very much again. We hope we meet us in the next seminars, and have a nice Friday. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.